Welcome to the AP Chemistry presentation on aqueous reactions. This presentation is aligned with Chapter 4 of the Brown-LeMay and Burston textbook, 9th edition. So, first of all, let's talk a little bit about what exactly is a solution. A solution is a homogeneous mixture of two or more substances. The substance that is in the greatest quantity is the solvent. The substance in lesser quantity is the solute, and a solution can have more than one solute. So just as an example, in a solution of sodium chloride in water, sodium chloride is the solute and water is the solvent. Now, most of the time in chemistry we're going to be dealing with aqueous solutions. So an aqueous solution is one in which water is the solvent. And aqueous solutions are so common that most of the time when chemists say solution, they really mean aqueous solution. In order to understand what exactly happens in the process of making a solution, you first have to understand that each type of compound, molecules, ionic compounds, and acids, dissolves through a different process. So the first thing we're going to do is look at each of these different processes. The first process we're going to look at is the process of dissolving ionic compounds. Soluble ionic compounds first dissociate and then they hydrate. Now, if you just look at what you start with and what you end with, what you end up with is a reaction much like these three that I've shown here. What you start out with is your solid ionic compound. What you end with is the individual ions in solution, hence the phase is marked as AQ. So if you start with some generic ionic compound AB, you end with the positively charged A's and the negatively charged B ions, and they are not attached to each other anymore. They are dissolved in the solution. To look at a more concrete example, if we took cesium nitrate solid, when you dissolve it in water, becomes aqueous cesium atoms and aqueous nitrate atoms. Similarly, sodium sulfate, if you take solid sodium sulfate and dissolve it in water, you end up with two aqueous sodium ions and one aqueous sulfate ion. And that's because for every sulfate ion, there are two sodium ions. So dissociation, I said there's these two processes, dissociation and hydration. Dissociation is breaking the lattice into the individual ions. And then hydration is the association of water molecules with these ions. You basically end up with a shield of water molecules. In order for ions to react, they have to shed this shield of water. In other words, if the ion has to react, it has to get the water out of the way first, and then the ion itself can take part in a reaction. And this can sometimes be an obstacle to reactions in aqueous solutions. Most of the time it's not something you have to worry about at the level of AP chemistry. But if you look at the overall reaction, going from AB solid to aqueous A ions and aqueous B ions, if you look at the overall reaction, you'll notice that there is only a one direction to the arrow. That's done on purpose, and that's because these reactions are one way. And the result of this one-way nature is that you permanently create mobile, charged particles. This will be an important thing to remember later on. Soluble ionic compounds permanently create mobile charged particles. Now this is a lot of words, so let's take a look at this as a graphic. So you'll notice that we start out here with the lattice of potassium and chloride ions, and as with any ionic compound, it happens as a crystal lattice, more or less the same thing, and crystalline means that it occurs in this repeating pattern of potassium, then a chlorine, then a potassium, then a chlorine. And this blue portion down here is some water, and water is of course made up of water molecules. I've shown a few water molecules, of course not all of them. You've got your red oxygen atoms, and with each red oxygen atom are 2 black hydrogen atoms. So looking at what happens next, the crystal is added to the water, and when it comes into contact with the water, it first dissociates. That nice, highly organized crystal no longer exists after the dissociation portion. Okay, so that is dissociation, going from the crystal to a random and disconnected array of ions. Now what happens next is that the water molecules move so that the oxygen end is surrounding the positively charged potassium ions, and the hydrogen end is surrounding the negatively charged chlorine ions. That's because something we'll learn later on in the course, but as a brief introduction, the oxygen end of water is slightly negatively charged, so it's attracted to the positively charged potassium ions, and the hydrogen end is slightly positively charged, so it's attracted to the negative chlorine ions. So what you see now is that each of the ions has this shield of water molecules around it, and so this is the hydration phase. Now, to look at this as a cartoon, that was kind of complicated, but let's look at it one more time in sort of stages and distinguish once again which constitutes each stage. Again, before the water and the ionic compound come into contact, you have just a nice, highly organized crystal of potassium and chlorine, or any other pair of ions. Crystal gets dropped into the water. Crystal goes from the crystal lattice falls apart, and you end up with randomly arranged ions. That part is called dissociation. So from crystal to randomly arranged ions, dissociation. Next, the water molecules cluster around the ions. That portion is called hydration. Now, just to make things really nice and complicated, chemists do not always distinguish these two separate steps, the dissociation from the hydration. Sometimes the whole process is called dissociation. So dissociation can have multiple meanings. The first is just breaking up the crystal lattice and resulting in randomly arranged ions. The other is not only doing the breaking up of the crystal lattice, but also the association of water molecules with these now dissociated ions. You just have to read out through the context of the sentence as to what exactly the speaker means. Alright, so that's the process of dissolving ions. Let's look at dissolving molecules. Molecules do not break apart, or at least usually they do not break apart. So really all you have is the change of phase. You start with the M, which is the molecule, and it's in some phase other than aqueous. That would be liquid, solid, or gas. And then afterwards you end with the exact same thing, but now it's in the aqueous phase. So, as I said before, only the phase changes. Now, molecules, once the molecules are in the aqueous phase, they will be mobile. They can move throughout the solution, but there are no charged particles. You notice it in the on the M here, there is no charge. So that means there is no dissociation. And again, there's a few random exceptions, but you don't need to know about that. So let's look at a few examples. CH4O, which is a not particularly good way of writing methanol, starts out as a liquid, like most alcohols with a small number of carbons. It can dissolve in water easily, so you start out with liquid methanol, you drop it into water, and you end up with aqueous methanol. Same thing with C6H12O6, that's glucose. Starts out as a sugar when it's not in contact with water. Add it to water, stir it up a little bit, you end up with the same molecule, except now it's in the aqueous solution. There are also a few gases that can dissolve. Oxygen is one of them. If you start out with oxygen gas and say you bubble it through the water or something like that, you will get some aqueous oxygen. Same molecule, just a different phase. Okay, I said usually a lot in the last slide. Usually you don't end up with ions. Usually there's no dissociation. And the reason I said usually is because there is one very important exception, which is ammonia, NH3. Now, ammonia is a weak base. We'll get into acids and bases later on in this presentation, but ammonia is a weak base, and that means well, in order to understand what weak bases are, let's talk about strong bases first. Strong bases are soluble ionic hydroxides. So that means they have the OH minus ion as part of them. And since they're soluble, and since they're ionic, referring back to previous slides, they would undergo a one-way reaction to form OH minus, as well as a positively charged ion. So a simple example of a strong base, again this is a strong base, not a weak base, is KOH. That's a solid potassium hydroxide, and when you dissolve this in water, it turns into aqueous potassium ions and aqueous hydroxide ions. In other words, it dissociates. So that's what a strong base is, a soluble ionic hydroxide. A weak base undergoes a two-way reaction to form hydroxide ions. So what both strong and weak bases have in common is that they form hydroxide ions, but strong bases do it with a one-way reaction, weak bases do it in a two-way reaction. So, for example, ammonia, which is the most important weak base for the purposes of AP chemistry. Ammonia reacts with water, and the water loses a hydrogen ion, and the ammonia gains a hydrogen ion. The result is that ammonia becomes the ammonium ion, and that's aqueous, and the water loses a H plus ion, and so you're left with the OH minus ion, or the hydroxide ion. And remember, this reaction is continuously happening in both directions. You always have ammonia and water reacting to form ammonium and hydroxide, and then when ammonium and hydroxide can get together, the reaction goes in the opposite direction, and you end up with ammonia and water. So the result of all this is that you only temporarily form charged particles. Okay, so molecules, just a change of phase unless you're dealing with ammonia, in which case you end up with ammonium and hydroxide ions. Or actually you end up with an equilibrium between ammonia and water on one side and ammonium and hydroxide ions on the other side. Let's talk about acids. Just as there's strong and weak bases, you got strong and weak acids. Let's talk about strong acids first. Strong acids dissociate completely. So if you start out with a hydrogen ion and some cation, which are the two parts that you need for an acid, that undergoes a one-way reaction to form hydrogen ions and your anion. So your acid molecules break up into hydrogen ions and anions. You're in a strong acid, your anions and hydrogen ions never get back together and form the original acid molecule. So weak acids only partially dissociate. It's the same sort of dichotomy we saw with strong versus weak bases. So weak acids only partially dissociate. They are constantly dissociating and reassociating while in solution. So your HX is constantly breaking up into H plus and X minus. Your X minus and H plus are constantly getting back together to form HX ions. Sorry, HX molecules. Being a strong or weak acid has nothing to do with concentration or corrosive power. You can find some incredibly dangerous, incredibly corrosive, incredibly high concentration acids that are nevertheless considered weak acids. So the only distinction between a strong and a weak acid is this one-way dissociation in strong acids, two-way dissociation in weak acids. Okay, so how do you know which acids are strong and which acids are weak? Well, there's a list of strong acids and their dissociation reactions. All right, you got hydrochloric acid. That dissociates into H plus and Cl minus. Hydrobromic acid. That dissociates into H plus and Br minus. Hydroiodic acid. That breaks up into H plus and I minus. Let's see, that's from a chlorate ion, so the 8s become us, so this would be chlorous acid. No, wait, the 8s become X, so this would be chloric acid. And that breaks up into hydrogen ions and chlorate ions. Perchloric acid, nitric acid, and sulfuric acid. Now, pay attention. In sulfuric acid, only the first hydrogen ion dissociates completely. There's 2 hydrogen ions in sulfuric acid, only the first one dissociates completely. So what you end up with in a sulfuric acid solution is not hydrogen ions and sulfate ions. You end up with hydrogen ions and bisulfate ions, not sulfate ions. This is a very common mistake. Okay. So, if you run across an acid and it's not on this list of hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric acid, perchloric acid, nitric acid, and sulfuric acid, if it's not one of those, it's a weak acid. And the only way to know what the strong acids are is to memorize this list of strong acids. Now, just to make life a little easier on you, the 3 most common strong acids encountered in AP chemistry are hydrochloric, nitric, and sulfuric acids. Remember that those 3 are strong acids, and about 75% of the time you'll be able to distinguish your strong acids from your weak acids. Of course, if it's the other 25% of the time, then it helps to know the full list. Okay, so the process of dissolving, we already talked about the process of dissolving a weak acid. The process of dissolving a strong acid is this one-way reaction that goes from your acid molecules to hydrogen ions and anions, whatever the anion may be. It's basically the same process as dissolving soluble ionic compounds, and much like dissolving soluble ionic compounds, you have dissociation, which in this case is the breaking apart from the molecule into the ions, and hydration, which is association of water molecules with the resulting ions. Just like with soluble ionic compounds, this is a one-way process that ends up creating ions. So just like with soluble ionic compounds, you permanently create mobile charged particles. Alright, weak acids, talked about this a little bit already, but weak acids have this two-way reaction. And so you have what is called partial dissociation and hydration. So you form ions from the molecules, and also you form molecules from the ions. And what this does is it only temporarily creates mobile charged particles. You've got mobile charged particles, but they don't stick around. And the reason they don't stick around is because of the reverse reaction. Your ions can react to form something that is not charged. Mobile, but not charged. Okay, so some examples include hydrofluoric acid. Hydrofluoric acid partially dissociates into hydrogen ions and fluorine ions. Then your hydrogen and fluorine ions get back together to form hydrofluoric acid molecules. Acetic acid. Acetic acid dissociates into hydrogen ions and acetate ions. And in a solution of acetic acid, you have your acetate ions and your hydrogen ions reforming back into acetic acid molecules. Alright, so we've covered quite a bit of material so far. We're about 22 minutes into this presentation. So let's try to summarize what we got so far. Okay, so ionic compounds undergo this one-way dissociation. It separates from an ionic solid into individual ions, and what that results in is that it permanently creates charged particles. Strong acids basically do the same thing. You start out with a molecule, you end with ions and ions only, and this also permanently creates charged particles. Weak bases undergo this two-way reaction, and again, the only weak base that you really have to worry about for this class is going to be ammonia. So your ammonia and your water react to form ammonium and hydroxide. Meanwhile, your ammonium and your hydroxide are reacting back to form ammonia and water molecules. The result of this is that you temporarily create charged particles. Weak acids also have a two-way reaction. Your acid molecule dissociates into hydrogen ions and anions, and so just like weak bases temporarily created charged particles, weak acids also temporarily create charged particles. Last but certainly not least, molecules just change phase. Molecules themselves have no charge, so you have no charged particles that are created when a molecule dissolves in water. Okay, so how do we know that this dissociation thing actually happens? The whole dissociation and hydration thing happens one way with ionic compounds and strong acids, two ways with weak bases and weak acids. Our evidence for this consists of a conductivity test. Now, in order to understand a conductivity test, you have to understand electricity a little bit. A conductivity test asks, does a solution conduct electricity? And what it consists of is a aqueous solution, and you put two electrical wires in them, or electrical leads, basically the same thing. And usually you hook this up to a light bulb. And then the leads and the open circuit of the light bulb is connected to a power source. Now, like I said, you got to understand a little bit about electricity. And there's two properties of electric circuits that you need to understand. The first one is called current. Current is created by the movement of charged particles. And in order to light up this light bulb here, you would have to have current. And in order to have current, we have to have charged particles that can move through the solution. No charged particles means no current. The next property of electric circuits to understand is what's called resistance. So the charged particles might be able to move, but if there's something that resists that movement, that's logically called resistance. Now, in a solution, the resistance comes from the charged particles combining to make neutral molecules. So any process, it'll start with charged particles and end with something that's not a charged particle, will create resistance. If you have higher resistance, then the light will still light up, but it will be dim. Okay, so let's look at the conductivity test results that we, at least in theory, should get if we dissolve an ionic solute or a strong acid. So two examples of this would be potassium chloride. Potassium chloride undergoes this one-way reaction to create potassium ions and chloride ions. Afterwards, there's no potassium chloride left over. It's all just potassium ions and chloride ions. Similarly, hydrochloric acid breaks up into hydrogen ions and chloride ions in a one-way reaction. Okay, so we'll have, for example, potassium ions and chloride ions in our potassium chloride solution. And when we fire this thing up, when we attach the conductivity tester, the charged particles can carry current, right? Current is the movement of charged particles. So we have charged particles. The fact that they're in solution means that they can move, so we will have current. And the one-way nature of this chemical reaction means that the circuit will have very little resistance. So we got current, we got hardly any resistance. That means that the potassium ions will be attracted towards the negative terminal because they have positive charge, and the chloride ions will be attracted to the negative terminal. That will result in the bulb lighting up. Alright, so since ionic compounds and strong acids carry current with very little resistance, or they allow a solution to carry current with very little resistance, they are called strong electrolytes. So, strong electrolytes are ionic solutes and ionic compounds and strong acids. Alright, let's look at weak bases and weak acids. For example, hydrofluoric acid dissociates into hydrogen and fluoride ions, but since it's a weak acid, the hydrogen and fluoride ions react backwards to form hydrofluoric acid molecules. Same thing with ammonia. Ammonia, no charge, and water, no charge, react to form ammonium, which does have charge, and hydroxide, which also has charge. Meanwhile, the two charged particles can also react with each other to form the uncharged particles. Okay, so if we look at hydrofluoric acid, for example, we have hydrogen ions and fluoride ions. And the fluoride ions will be attracted to the positive terminal, and the hydrogen ions will be attracted to the negative terminal once we put some power on here, which I seem to have neglected. Alright, however, that's one of two things that the hydrogen and fluoride ions can do. They can be attracted to the electrode with the opposite charge. The other thing they can do is they can react with each other to form an HF molecule, and that HF molecule is not attracted to either electrode. And since it's not attracted to either electrode, and since it doesn't have charge, the HF molecules can't carry current. So when we hook this up, the light will be dim because this chemical reaction of our charged particles creating uncharged particles will present some resistance. We will still get current because we have mobile ions, the F- going this way and the H+ going this way. but we will also have significant resistance. Okay, so the charged particles mean we can carry current. The two-way nature of the reaction means that we encounter significant resistance. The result of all of this is that we have low conductivity, or we have a dim bulb. So, since we get some conductance, but it's not real strong, this is called a weak electrolyte. So, your weak electrolytes are weak bases and weak acids. Okay, let's look at molecular solutes. For example, oxygen. Oxygen gas can be dissolved in water in limited quantities. So if we have oxygen gas molecules here, they have no charge. And since they have no charge, they will not be attracted to either electrode once the power gets turned on. So we turn on the power, and nothing. Okay? No charged particles means no current. No current means no light. No current means no conductivity. So, since these things are non-conductive, molecular solutes are non-conductive, they are called non-electrolytes. So, your non-electrolytes are the same thing as molecular solutes. Okay, so we're at about the half-hour mark here. Let's do another summary. You got your ionic compounds, your strong acids, your weak bases, your weak acids, and your molecules. All of them can be solutes. Let's look at their electrolyte behavior. Your ionic compounds and your strong acids are both strong electrolytes. All strong acids are strong electrolytes. All soluble ionic compounds are strong electrolytes. Your weak acids and your weak bases are both weak electrolytes. All weak acids are weak electrolytes. All weak bases are weak electrolytes. Your molecules, all molecular solids, are non-electrolytes, with the exception of those that form weak bases, specifically ammonia. Alright, now I know this slide is titled Summary, but I'm going to add some additional information to it. We talked about acids and bases, so along with that goes the concept of pH. So some ionic compounds are basic, and that means they have a pH, when they're dissolved in water, they have a pH greater than 7. Okay, pH greater than 7 means that they're basic. The specific ions, the specific anions that cause that are basic solutes are hydroxide, sulfide, oxide, carbonate, and bicarbonate. These all 5 of these ions create solutions which are basic, solutions which have a pH greater than 7. Now, there's another ion, ammonium, which is acidic. Ammonium, if your solution contains an ammonium ion, then your pH is going to be less than 7. pH less than 7 means that you have an acidic solution. And for all other soluble ionic compounds, your pH is going to be 7. Strong acids and weak acids are, for obvious reasons, both acidic. And so their pH is going to be in the acidic range, namely less than 7. Your weak bases are obviously going to be basic. In other words, ammonia forms a basic solution, and so that's going to have a pH greater than 7. Again, pH greater than 7, basic, pH less than 7, acidic. Molecules are going to have a pH of 7. When you have a solution with a molecular solute that is not a weak acid, nor is it a weak base, your pH will be 7. Okay, so let's apply these principles. Let's say you have 5 vials. They contain solutions of hydrofluoric acid, hydrochloric acid, sodium chloride, methanol, and potassium hydroxide. But you do not know which one is which. Each vial contains only one solute. Mr. Tom gives you a conductivity meter and a pH meter. After testing the 5 compounds, you must drink one of them. Good luck. Now, if you're going to drink something and you don't exactly know what it is, but you know what it might be, it's a good idea to know what exactly each of these does. So, HF, hydrofluoric acid, is pretty much the most, well, to my knowledge, it is the most corrosive acid around. You use it for etching things like titanium and very high grades of stainless steel. Dangerous as hell. Hydrochloric acid also is very dangerous, very corrosive. Sodium chloride is table salt. It is essentially harmless. It's about as harmless as chemicals get. Methanol is sometimes called wood alcohol. It will, in low quantities, make you drunk, in slightly higher quantities make you blind, and in even slightly higher quantities than that, it will kill you. Potassium hydroxide is a strong base. Strong bases are arguably more dangerous than strong acids. So, potassium hydroxide will, when it comes into contact with human tissue, it turns it into this kind of gooey jello-like stuff that kind of peels off. So, potassium hydroxide is also really dangerous stuff. You don't want to drink it. So, out of all of these, the one you want to find is the sodium chloride. Okay, so, you only have your pH meter and your conductivity meter. Let's look at your results. Okay, vial A, and you don't know what's in vial A, but its pH is 2, and the conductivity meter says it's a weak electrolyte. It has low, but not zero, conductivity. Your vial B has a pH of 7, again, neither acidic nor basic, and it's a strong electrolyte. Vial C has a pH of 7, it's a non-electrolyte. Vial D has a pH of 2, that's on the acidic side, and it's a strong electrolyte. Vial E has a pH of 14, highly basic, and it's a strong electrolyte. And just as a reminder, the options you have to choose from are hydrofluoric acid, hydrochloric acid, sodium chloride, methanol, and potassium hydroxide. So, at this point, I suggest you pause the presentation and think about which combination of properties would be characteristic of each of the possible solutes. Okay, I hope by now you've figured it out. Vial A is acidic, so that means it has to be either HF or HCl. Since it is a weak electrolyte, that means that this acid has to be a weak acid. HCl is a strong acid, so the only weak acid we've got here is HF. So vial A is going to be HF. Vial B has a neutral pH, and it is a strong electrolyte. So our strong electrolytes are hydrochloric acid, sodium chloride, and potassium hydroxide. Now, hydrochloric acid would have an acidic pH, and potassium hydroxide would have a basic pH. The only strong electrolyte with a neutral pH is sodium chloride. So vial B is what you want to go for. Vial C is a non-electrolyte with pH 7. The only non-electrolyte on the list is methanol. And so vial C has to be methanol. Vial D is a strong electrolyte, and it is on the acidic side. So between our two acids, HF and HCl, the only strong electrolyte is HCl. Again, strong acids are strong electrolytes. Okay, vial E is by process of elimination, potassium hydroxide. But if you look at it logically, it's basic, so that means it has to contain hydroxide ions, oxide ions, sulfide ions, carbonate ions, or bicarbonate ions. The only one that the only compound we have that contains one of those ions is potassium hydroxide. Okay, so by using very little information, we can identify some unknown substances. Okay, the whole reason I talked about dissociation and all of that is because the AP exam expects you to be very fluent with what's called a net ionic equation. So there are three ways to express a reaction which happens in solution. There's the molecular equations, which are what you've been, which is what you've been doing so far in this class. There is the complete ionic equation, and then there is the net ionic equation. Now, the College Board requires you to use net ionic equations on the reaction sections, and in fact, their net ionic equations, as well as molecular equations, are scattered all through the test, so you'd better know this stuff. In order to distinguish the three types of reactions, let's take a closer look at an example. Okay, let's say we start with silver nitrate and potassium chloride, both of them in solution. We have a beaker full of silver nitrate solution and a beaker full of potassium chloride, and we pour both of them into an even bigger beaker. The solubility rules I gave you a few classes ago tell you that silver chloride is going to be a solid. It does not dissolve in water. So in the process of making a net ionic equation, you really have to know your solubility rules. Chlorides are generally soluble. Silver is an exception to that. You also end up with potassium nitrate, which is soluble. Nitrate ions, anything with a nitrate ion is always soluble. Anything with an alkali metal ion is always soluble. No exceptions to either of those two rules. Okay, so we start out with silver ions and nitrate ions, both dissociated because this is in the aqueous phase. We also start out with potassium ions and chloride ions, again in the aqueous phase. That's before the reaction. After the reaction, we end up with solid silver chloride. And since silver chloride is a solid ionic compound, it forms a crystal lattice. We also end up with potassium ions and nitrate ions. Now, potassium nitrate is soluble, and so it's going to remain dissociated. So if we look at, well, first of all, the example up here, this line, is what you're used to seeing for a chemical reaction. That's called the molecular equation. Now, if we look at it on an ion by ion basis, we're going to have we're going to have silver ions, nitrate ions, potassium ions, and chloride ions. And these are going to be separated. They're going to be all dissociated when we start out. Afterwards, we're going to have associated silver and chloride ions, in other words, solid silver chloride. We're going to have dissociated potassium ions, in other words, aqueous potassium ions. We're going to have dissociated nitrate ions, in other words, aqueous nitrate ions. This line here is called the complete ionic equation. To go from the molecular equation to the complete ionic equation, you dissociate all the strong electrolytes. You dissociate anything that actually dissociates. And you keep associated, things like the silver chloride, anything which should remain associated. I'm just going to recopy that for a second, because if you look at this like an algebra equation, there's a lot of cases where we have x on both sides of the equation. We have nitrate on the product side as well as nitrate on the reactant side. We have potassium ions on the reactant side and also potassium ions on the product side. What this means is that the potassium ions and the nitrate ions do not change. Effectively, we can cancel them out of the equation because they actually do not participate in the reaction. They do not react. And so after we remove everything that cancels out, we end up with what's called the net ionic equation, which is only the ions that react. So the silver ions and the chloride ions get together to form silver chloride. That's really the only change between this image that we start out with and this image that we end up with, is the silver ions and the chloride ions have now grouped together to form silver chloride. Okay. So, once again, to reinforce that distinction, molecular equations, everything is associated. All compounds are associated even if they actually dissociate. So if we look at another reaction, silver acetate plus potassium chloride giving us silver chloride and potassium acetate, the complete ionic equation is you start with the balanced molecular equation and then you fully dissociate all your strong electrolytes are fully dissociated. If it doesn't dissociate completely, leave it associated. Now remember, things that dissociate but not completely are our weak electrolytes, our weak acids, and our weak bases. Anything that's solid, liquid, or gas, just leave it together. So, looking at what we got here, silver acetate. Acetate ions are always soluble, so that means that this will, and this is an ionic compound, soluble ionic compounds dissociate. Potassium chloride. Potassium is a soluble ionic compound, and again, it will dissociate. Silver chloride. Silver chloride is an insoluble ionic compound, so in the complete ionic equation, it will remain associated. Potassium acetate is soluble, so it will dissociate. So basically, everything it should be dissociated in this particular reaction, except for the silver chloride. So that's what we end up with. Okay, in the net ionic equation, you look at the complete ionic equation, and you cancel out ions that occur on both sides. These ions cancel out on both sides are called spectator ions. So we notice that we have acetate ions on both sides, and so we also have potassium ions on both sides. So the acetate ions and our potassium ions will be our spectator ions for this particular reaction. They will cancel out, and we will be left with this reaction down here, the net ionic equation, that silver and chloride get together to form silver chloride. Now notice that this is the same net ionic equation that we had on the previous slide, and that's because effectively the same thing, the same chemical change is happening. The only difference is the spectator ions. Okay, so it's easy to make mistakes on net ionic equations when you first experience them, so let me walk you through some of the common mistakes. Reminder number one is do not dissociate your weak acids. So looking at our familiar molecular equation, or half of a familiar molecular equation, we got silver acetate plus, this time we've got hydrochloric acid, and we're going to end up with silver chloride and acetic acid. Now, hopefully you remember which acids are strong acids. Hydrochloric acid is a strong acid, so we should dissociate that. But acetic acid is a weak acid, and so we should not dissociate that. Okay, so silver acetate, soluble ionic compound. So that's going to dissociate into silver ions and acetate ions. Hydrochloric acid is a strong acid, so it's going to dissociate completely into hydrogen ions and chloride ions. Silver chloride is a solid, so that does not dissociate at all. Acetic acid is a weak acid, so we do not write that as dissociated in the complete ionic equation. So in this case, let's see if anything cancels out in the net ionic equation, and surprise, surprise, it doesn't. So in this case, our complete ionic equation and our net ionic equation are the same. Let me reinforce a point I probably should have made earlier, which is that in going from the complete ionic equation to your net ionic equation, you only cancel out things that are exactly the same on both sides. That means same formula and the same charge. So, reminder number 2, don't dissociate your solids, your liquids, and your gases. So if we start with sodium bicarbonate, the active ingredient in baking soda, and react that with hydrobromic acid. Okay, so we've got a soluble ionic compound and a strong acid. This will react to form 3 things: sodium bromide, a soluble ionic compound; water, a liquid; and carbon dioxide, which is a gas. Now, remember that water is in the liquid phase, not in the aqueous phase. Water is not dissolved in water. Water is water, and that's why we say it's in the liquid phase. Okay, so complete ionic equation for this, we're going to dissociate our soluble ionic compound into sodium ions and bicarbonate ions. We're going to dissociate our strong acid into hydrogen ions and bromine ions. By the way, right there, right above my laser pointer, that's a negative sign. Doesn't come out too well in this font. Sodium bromide is a soluble ionic compound, so we're going to get sodium ions there and bromine ions there. Water is a liquid, so you do not dissociate the liquid. CO2 is a gas, so do not dissociate the gas. Now, let's look for things that we can cancel out to make the net ionic equation. Well, we got bromine ions on both sides. We got a bromine ion there and a bromine ion there, so that'll cancel out. We also have sodium ions. We got a sodium ion there and another sodium ion right there. So those should cancel out as well. Okay, sodium ions, bang, canceled out. Bromine ions, bang, canceled out. Yeah, we pay for expensive sound effects here at Bosco Tech. Alright, so what you end up with in the end is bicarbonate ions and hydrogen ions making water and CO2. Okay, reminder number 3. And this gets back to what I said way earlier when we were talking about acids. Don't dissociate the second acid from H2SO4. Don't dissociate the second acid from sulfuric acid. Okay. So let's look at a reaction involving sulfuric acid. Sulfuric acid plus barium chloride is going to make barium sulfate. And remember, barium sulfate is an exception to the rule that sulfates are soluble. Barium sulfate and 2 hydrochloric acid molecules. Well, it's really not a molecule, as I hope you realize. Okay, so the sulfuric acid is a strong acid, so we should, in the complete ionic equation, we should write it as 2 separate ions, but those 2 separate ions are going to be H plus and HSO4 minus. The second H does not completely dissociate, so we leave it stuck on to the sulfate to form bisulfate. Okay, so sulfuric acid dissociates into a hydrogen ion and a bisulfate ion. Barium chloride is a soluble barium ionic compound, and so that dissociates into barium ions, and since we have a 2 right here, see the subscript 2, that means for every barium ion we get 2 chloride ions. Now barium sulfate is a solid, so you do not dissociate the solids, and we end up with 2 hydrochloric acid molecules. Those dissociate into 2 hydrogen ions and 2 chloride ions. Okay. This slide also shows the effects of subscripts and coefficients that are not 1. Basically, when you go from the molecular reaction to the complete ionic reaction, you have to ask yourself, how many ions do I have? And for every 1 barium chloride, we end up with 1 barium and 2 chlorides. For every 2 hydrochloric acids, we end up, let me rephrase that. For every 1 hydrochloric acid, we end up with 1 hydrogen ion and 1 chloride ion. But since we have 2 hydrochloric acids, we end up with 2 hydrogen ions and 2 chloride ions. Okay, looking for things that cancel out of the complete ionic reaction. We have 1 hydrogen ion here and 2 hydrogen ions here. So we can subtract 1 hydrogen ion from each side, but that's not going to completely cancel out those hydrogen ions on the product side because we have 2 of them. Next up, we have 2 chloride ions on each side, so those will cancel each other out completely. This leaves you with a net ionic equation of the bisulfate ion plus barium ions react to form barium sulfate and hydrogen ions. Okay, reminder number 4. If everything cancels out of the complete ionic equation, then no reaction actually happened. This is commonly abbreviated NR. So let's look at a reaction like this. If we start with a balanced molecular reaction of 2 potassium nitrate ions and 1 barium chloride formula unit, we realize that this is a double replacement reaction, so our potassium pairs up with our chlorine and our barium pairs up with our nitrate. We end up with barium nitrate and 2 potassium chlorides. The complete ionic reaction, well, let's look at this. Potassium and nitrates are both always soluble, so 1 potassium nitrate will give us a potassium ion and a nitrate ion, but we have 2 potassium nitrate formula units here, and so that will give us 2 potassium ions and 2 nitrate ions. The barium chloride is soluble, so it will give us 1 barium ion and 2 chloride ions. The barium nitrate is soluble, again all nitrates are soluble, so that'll give us a barium ion and 2 nitrate ions. Notice the subscript 2 becomes a coefficient of 2 here, and each potassium chloride formula unit gives us a potassium ion and a chloride ion, and since we have 2 of these, we get twice as much of each. Now, let's start canceling things out. We have 2 potassium ions on each side. Those cancel each other out. We have 2 nitrate ions on each side. Those cancel each other out. We have 2 barium ions on each side. Those cancel each other out. And we have 2 chloride ions on each side. Those cancel each other out. The net result is nothing! Nothing happens when we mix these 2 solutions, a solution of potassium nitrate and a solution of barium chloride. So, if you wanted to write out the net ionic equation, you could say that 2 potassium ions plus 2 nitrate ions plus a barium ion plus 2 chloride ions gives you no reaction. Okay, so how is it that we're mixing chemicals, and when we look at it one way, in other words, as a molecular reaction, it kind of looks like we have a reaction, but when we actually look at it in more detail, we, in reality, have no reaction. So looking at this graphically the same way we did before, in potassium nitrate, you have potassium ions and nitrate ions. You also have barium ions and chloride ions. Afterwards, you have barium nitrate, which is actually in the form of barium ions and nitrate ions. You also have potassium chloride, which is in the form of potassium ions and chloride ions. Now, look at the two blue boxes. They're the same. Nothing changed. No change occurs. And since no chemical change occurs, that means we have no reaction. Okay, so to summarize our portion, our discussion of net ionic equations, in the molecular equation, everything is together. Everything is associated. In the complete ionic equation, you have to start with the balanced molecular equation, and then you break apart all the strong electrolytes. You dissociate all the strong electrolytes, and just a reminder, the strong electrolytes are going to be your soluble ionic compounds and your strong acids. You got to memorize the list of strong acids, and you got to memorize your solubility rules in order to do this step right. With the net ionic equation, you cancel out your spectator ions from the complete ionic equation. This means that in order to make a net ionic equation, you have to have your complete ionic equation first. And in order to have your complete ionic equation, you have to have a balanced molecular equation first. Okay, that's the end of this presentation. Oh, no, it is not the end of this presentation. Okay. Well, this lecture, this presentation was designed for an in-class presentation, but it actually works very well as an out-of-class practice. Work with the work by yourself to determine the net ionic equation for the following molecular reactions. Okay, go ahead. Get out a piece of paper. Yes, get out a piece of paper and actually do this. I know you Bosco Tech students are trying to stall and just push the forward button and do whatever you can to not do the practice, but as with everything in AP Chemistry, practice really helps. So, pause the video for a second, take a few seconds to try to work out the net ionic reactions for each of these. Okay, hopefully you paused it and worked things out. Let's look at the first one. All right. Okay, this looks a little unusual. Okay, so the first thing is, notice that I did not balance the molecular reaction. You need 6 HIs, and the iodine cancels out as the spectator ion. Okay, so you had to have a coefficient of 6 here and a coefficient of 2 here in your balanced molecular equation. And the hydrogen iodide is where we got the H+ ions from. The iron is a solid, so it does not dissociate. The iron 3 iodide is a soluble ionic compound, so it dissociates. The hydrogen is a gas, so it does not dissociate. Your spectator ions, again, in this case, were the iodide ions. So you can do net ionic equations for single replacement reactions, too. All right, next up. Now that you know to check to make sure that I gave you a balanced molecular equation, look at this. All right, copper there, 1 copper there, 2 nitrates there, 2 nitrates there, 1 magnesium there, 1 magnesium there. Okay, so this is a balanced molecular equation. Net ionic equation that you have left over is the copper ions and the magnesium metal form copper metal and magnesium ions. Okay, the nitrate is unchanged. The nitrate is our spectator ion, and so it cancels out of this reaction. You might be tempted to cancel out the copper 2 with the copper metal. Remember, you only cancel out if the two substances have the same formula and the same charge. Copper ions, the copper 2 ion and the copper metal, have the same formula, but they do not have the same charge, and so you cannot cancel them out. Alright, lead acetate. Again, you actually have an unbalanced reaction. You actually need a 2 right there. And so your net ionic equation here is going to be that the lead 2 ion reacts with 2 iodide ions to form lead 2 iodide. The potassium ions and your acetate ions are always going to be they will always be spectator ions because they are, well, no, they won't always be spectator ions. I just thought of an exception. Anyway, so if you actually write out the complete ionic equation and then cancel out, you'll notice that you have acetate ions on both sides and potassium ions on both sides. Okay, last option is this one. Hopefully you will recognize this as a non-trivial redox reaction, except it is written in molecular reaction form. It is, I did you a favor and I balanced this. I won't necessarily be doing you favors on the next test, but the potassium iodide, that dissociates. Potassium permanganate, that dissociates. Hydrochloric acid, that's a strong acid, so that dissociates too. Iodine, that does not dissociate. Manganese 4 oxide does not dissociate. Potassium chloride does dissociate. Sodium chloride does dissociate. Water is a liquid, so it does not dissociate. And once you cancel out the stuff that occurs on both sides of the reaction, you end up with this. Your spectator ions were the sodium ions, the potassium ions, and the chloride ions. What you're left with is that iodide ions plus hydrogen ions plus permanganate ions creates elemental iodine, manganese 4 oxide, and some water.